Now I have one more example of using the exponential to solve a differential equation. And this is actually one that's going to be using that we're going to get a defective matrix for. So unfortunately, computing the exponential for this problem is going to get a little bit more complicated than I originally intended for it to do. And so you need to actually end up playing around with the power series to figure out what the entries of our exponential should be. So I decided to put this as its own bonus video. I'm not going to require you to watch this video since there actually won't be any problems that I'm asking you to solve using defective matrices. But the results of this turn out pretty interesting, so I do want to go ahead and do it. So we have this second order differential equation. Y double prime is 2 times y prime minus y, where we know where its initial value problem, we know where y starts and we know where y prime starts. Now, we actually the way that we actually know how to solve second order systems is to actually introduce more functions. I'm going to rename y as y1, and then I'm going to introduce y2 as the derivative of y1. That means that we essentially turn our system into y1 prime is equal to y2. That's just this equation here. And then y2 prime, well, y2 prime is y1 double prime, so it's y double prime. So we get a negative y1 and then a plus 2 times, well, y prime is y2. And then this means that y1 of 0 is 1, y2 of 0 is negative 1. So we get our a here is 0, 1, negative 1, 2. Our y0 is 1, negative 1. And we're going to try to solve this the same way that we were solving the other ones, by using the exponential. Now, of course, first we want to show that we can't diagonalize this. If we could diagonalize it, then we could do it the same techniques that we used in 6.2, and in fact we could find the exponential a lot easier. So let's actually find the eigenvalues of a. So we have subtract lambda from each of our diagonal elements. We go ahead and find this determinant. And we just end up with lambda squared minus 2 lambda plus 1. Or in other words, we have lambda minus 1 squared, which we want to equal to 0. So lambda is going to be 1. That's the only eigenvalue. So lambda equals 1. We go ahead and look at our matrix, but subtract 1 from our diagonal elements. We have negative 1, 1, negative 1, 1, which turns into negative, or actually, let's make this a positive 1, negative 1, and then we can cancel out that row. So we do have an eigenvector of 1, 1, but every other eigenvector is a multiple of 1, 1. So all the eigenvectors are, you can say, alpha, alpha for some real number alpha. We do not get two independent eigenvectors, so this is definitely defective. So let's actually try to find the exponential for this thing. We're going to look at the powers of a, because those are what we need to actually put into our formula for the exponential. So I'm going to save you the work of actually working to finding what these are, but it turns out that a squared is negative 1, 2, negative 2, 3. A cubed is negative 2, 3, negative 3, 4. A to the fourth is negative 3, 4, negative 4, 5, and so on and so forth. In fact, a to the n, right? Yeah, I'll go ahead and use n. A to the n is going to be negative n plus 1, n, negative n, and n plus 1. Okay, so we have a formula for a to the n, but getting that formula is already kind of a pain. We had to actually work out some examples, notice a pattern, and then we had to prove that this pattern does hold. We'd have to take this matrix, multiply it by a, and show that the next one still follows the pattern just for n plus 1. That's called induction, that process of doing that. Then we have to go and take these and put them into our formula. We have e to the ta is I plus ta plus 1 over 2 factorial, say t squared a squared, plus 1 over 3 factorial t cubed a cubed, and so on and so forth. Now we have to actually put all these matrices times the various powers of t into one big matrix. So maybe I should go ahead and copy this over to the other page. So what do we get? We get a big matrix where each of our, well, it's not really a big matrix necessarily. It's still a 2 by 2 matrix, but each of our elements is going to be a series. In fact, a power series. Our first one here, we have this one from the I. Then we have t times a. Remember, a has a 0 in that first spot, so that goes away. Then we have 1 over 2 factorial t squared times the negative 1 that we have in a squared. Then we have a 1 over 3 factorial t cubed times the negative 2 that we have in a cubed, and so on and so forth. So let me just kind of write this out. We have 1 minus 1 over 2 factorial t squared minus 2 over 3 factorial t cubed minus 3 over 4 factorial times t to the fourth, and so on and so forth. This never technically stops. We do very similar things in the other slots. So the I doesn't contribute to the second slot over here, but all the other ones do. In fact, they go as 1, 2, 3, 4, and so on. So nice pattern there. But we still have all the other stuff. We still have all the t's. So we end up getting a t plus, we have a 2 from the a squared, so we have 2 over 2 factorial t squared. We have a 3 over 3 factorial t cubed, 4 over 4 factorial t to the fourth, and so on and so forth. Same kind of thing down here. In fact, this one's even very similar to the previous one because all these that we have in that slot are exactly the negatives that we had in the other corner. So we actually get the exact same thing that we have over here, but with the negatives in front of everything. So negative t minus 2 over 2 factorial t squared minus 3 over 3 factorial t cubed minus 4 over 4 factorial t to the fourth, and so on and so forth. And then finally, now we have the pattern 2, 3, 4, 5. And we do have a 1 from the identity matrix as well. So down here we get a 1 plus a 2t plus a 3 over 2 factorial t squared plus a 4 over 3 factorial t cubed, plus a 5 over 4 factorial t to the fourth, and so on and so forth. And now comes the most fun part of it of all. We have to figure out what these power series actually represent. And that takes some work. I'm not going to go through all the work here. This is kind of a Calc 2 type question, though it's actually a little bit more complicated than I would give to a Calc 2 class. But it turns out if you just do stuff with derivatives and integrals of series and look at what the sum of various series are and try to recognize them as being the correct form for e to the t in various cases, This first part turns out to be e to the t minus t e to the t. The second one over here is t e to the t, which you can actually see because this was negative times that, this will be negative t e to the t. And then finally this one down here turns out to be e to the t plus t e to the t. So, not the easiest thing to do, but we have the exponential now. And that's really all the main work that we need to do to solve this problem. So remember, y is going to be e to the ta times y naught. So this matrix that we have here times our y naught. Y naught was negative 1, or sorry, 1, negative 1. We can work that out. Our first entry, when we take this minus that, we end up with an e to the t minus 2t e to the t. Then we have this minus that. We end up with a negative e to the t minus 2t e to the t. And so what does this mean? This means that our original y of t, is the first function, e to the t minus 2t e to the t. And then its derivative is negative e to the t minus 2t e to the t. And if you differentiate that, you can see that that's true. This is a function that satisfies this differential equation. The second derivative is 2 times the first derivative minus the original function. If you plug in 0, you get 1. If we differentiate it, then plug in 0, you get negative 1. And it's actually the only function that has that result. If you take differential equations, you'll see that there is another way of tackling this problem that avoids having to mess with power series. But at least one thing is very clear. We have a t e to the t. That is not something that we could have gotten using our techniques in 6.2. This is, again, something that is clearly from the fact that we have a defective matrix. That defective matrix has a big effect on what possible solutions we can get out of this process. And again, if you have taken differential equations, you might recognize why we got a t e to the t and not just something that has an exponential sign or a cosine. It comes from this fact that we have this repeated eigenvalue. The fact that this quadratic that we got has a repeated root. It all is based off of that. So that's what it is. There's not a lot more to say about it. Just be aware that I'm not going to be asking you to do any of this kind of stuff, either on the exam or even in your homework. This is a little bit off track. I'm not wanting you to worry about having to deal with power series or anything of that nature. Any of the problems that you're going to be doing in your homework are going to be using diagonalizable matrices, and so they'll be, you just find them the way that we did the first example of an exponential, and then I'm not going to be asking you about those on the exam. We're not solving any differential equations on the exam. So put your mind at ease on that part. So I'm going to go ahead and leave it there. Thank you for watching, and let me know if you have any questions about any of this stuff. But this is our last video, so see ya.